السلام عليكم شباب.
So today, inshallah, we will continue on a bit of introduction.
So more introduction into the material. The slides are adapted from the author of the book. He has already some slides for the book, Razavi, and he works at UCLA. So that's just for the credit of the origin of these slides. What will we discuss today quickly is kind of an introductory part. What is the main challenge in the wireless world that we have or we live in right now? And then accordingly, we will draw the challenges in RF design. And we will give, based on those challenges, we will give a big picture of what we will go through in this course in terms of RF wireless communication systems and the RF transceiver architectures in general. Okay. First part might be a bit stereotypic, but it's important to keep in mind. So currently we live in a world where we have almost everything is connected wirelessly. Forget about the microwave ovens. They generate wireless signal, but they're not connected wirelessly. But we have laptops, cameras that are connected to Wi-Fi or Bluetooth, camcorders, video cameras, cell phones, printers, TVs, where the origin, so the TVs, and then before that the radio was the original almost only existing wireless system. At that time, or the time of the TVs and the radio, not too many users, and the requirements in terms of speed was not that much. But with the growth of the usages, different application requirements, and the mixture of all of these, we ended up actually for an increasing need of high-speed wireless communication. And that high speed itself is a big challenge in terms of RF design. So with the added usages and more multiplexing, you can call it, we ended up with the need for high-speed wireless communication. This slide shows the story from a slightly different perspective. It's not a very recent one, so it stops at 2010, but you can imagine if we reach 2023 now, there is almost a double increase in terms of the frequency ranges that we are dealing with, but you will see that in terms of the technology, the increase has not been able to keep up. So what exactly does this slide look at? Here we have the different years, and on this side we have the frequency range that we are working on. Typically, a signal will have a range of frequencies, but we are talking about the center of that frequency, or the middle point of that frequency. So we have been increasing this. This is in gigahertz, so from below 1 gig until we are reaching now even terahertz of frequencies. Now you can see the growth as we go over the years. The growth has been almost linearly, and it continues in the same direction. There is another curve here, which is showing you the technology in terms of the integrated circuit technology. So the integrated circuit technology is always identified by a measure that tells what's the smallest device size that you can implement in that technology. In 95, we were talking about 0.5 micrometer. That's the smallest device. Now, as we reached 2010, we have been talking about 40 nanometers. Nowadays, we are talking about 0.28 nanometers. So you can see that the curve here is kind of reaching a saturation, because now the device level is becoming very close to the atomic level, and we cannot really go below that. We cannot break, so far, cannot break the atom and use that as a device in electronics. Okay, so that's why even though the demand of higher speed and smaller size keeps on increasing, but the technology is kind of not really keeping up anymore. What will happen after that? People talking about quantum devices, and then maybe something else in the future, we don't know yet. But anyways, this shows that, again, the challenge here is going to be not only that we want to reach higher frequencies, But as we go into smaller devices, right, we are, of course, making our devices more portable, but this comes with other challenges that we will see in the next couple of slides. Things related to power dissipation in these devices, how much power dissipation they can actually carry, how can we control the power dissipation, the linearity of the operation of the devices, and so on. So there are many challenges coming from this trend going into smaller and smaller and smaller devices as we move on. Okay. So here we can look at those challenges that faces the RF design process in general. The first general challenge is the fact that when we are dealing with RF electronics design, we are dealing with a domain that requires knowledge from many other disciplines or many other domains in the electrical engineering specialty, right? So you need to know a little bit about communication because you are doing devices for communication. You need to know a little bit about signals, whether propagation or randomness or how to represent signals and so on. You need to know a little bit about electronics. We are not going to go into all of these as we go through, but these are the aspects that an RF design engineer has to keep in mind while designing a particular chip or a particular RF circuit, let's say. Okay? So that's one challenge, the multidisciplinarity. You need to really combine knowledge from many domains in order to be able to work in this area. We have discussed this a little bit last time as well, so we have given some introductory part to this. In addition, there is the other aspect, which is the design trade-offs. Most of you have been through a senior design, right? So either the design course 428 or your own senior design courses, right? You haven't been? Not senior design even? Okay. Outside. Okay. So you know what's a trade-off, right? Typically, you have to pay something to get something in return. I want to go to the market and buy the most comfortable chair, okay? I like it really very nice, looks nice, it's very comfortable, okay, but it's very expensive. So now I have to figure out how to trade off this, right? If I want the nicest one, I'm gonna really impact my pocket money a lot. And if I go for the cheaper one, I might end up choosing a chair which is not comfortable at all and might hurt my back. So now you need to trade off. Maybe I will get something which is just comfortable, but affordable. So I give up some of the comfort and some of the cost in order to get some design, some product that fits my needs right now, right? Same thing, when you are designing an RF circuit, these are the things that you have to trade off in between. Noise is always there in any electronics. In order to make the noise less, you need to go for higher quality electronics. Probably you cannot go for very small devices. Typically they might have more noise, right? So maybe you need to go to a little bit bigger devices. Bigger devices are typically tending to consume more power. And also to overcome the effect of noise in general without changing the device, you can increase the transmit power. But generally you want a power efficient device, because if it's battery operated, for example, if it consumes a lot of power, then this means that you will have to recharge the battery every half an hour, right? That's not acceptable by the user. So in order to reduce power consumption, you have to take on a little bit more of the noise effect, right? So that's a trade-off. Also, with higher frequency, why do you want higher frequency? Because typically it gives you more transmission rate. So it gives you higher speed, right? But with higher frequency, in order to operate with reasonable performance, so less noise, you have to, again, pay more power. Because the bigger the frequency, the more noise you incur into your circuits, right? So that's a trade-off, right? Gain, you want your signal to reach as far as possible, right? So you need to put a lot of gain into your signals, whether it's inside an electronic device or even when it's transmitted. But again, higher gain typically means more power, sometimes means more noise, right? So again, a trade-off and so on, right? Supply voltage, does anyone know why we need to reduce the supply voltage other than power? Yeah, why?
Safety
So current is close to the answer.
Protection of electronics.
Hmm?
Protection of electronics.
Yeah, يعني مثلا why, for example, when you learned your digital electronics, you have been a lot talking about 5 volt as VCC, right?
For going from, like, if you want to go from 0 to like.
That's for digital. That's for digital. But now for analog electronics, typically the trend is to reduce. You want the supply voltage to be 3. Newer technologies are working at 2.7, 2.5, or 2.3 voltage. Why? Why do you want to reduce the voltage, the DC voltage supply to your
DC
circuit?
offset.
It's easier to
لا.
generate.
It has to do with current. What does current cause? Huh?
Bias current.
Oh, heat.
Heat. So the higher the voltage supply, the more you will have heat dissipation inside your circuitry. And typically, in RF electronics and in analog electronics in general, you try to work with less supply voltage. But again, the challenge is, with less supply voltage means that your signal is generally weaker, which means that it's more prone to noise effect, right? So that's a trade-off. But typically, you will find that newer technologies in analog electronics tries more and more to work with less supply voltage, okay? Again, if you reduce supply voltage, why does this affect your linearity? Can anyone figure out? If I reduce the supply voltage, I'm more susceptible to non-linearity. Why?
Saturation.
Exactly, because of saturation. Because eventually your amplifiers will not be able to produce something beyond what the supply DC gives. And if you want to amplify a signal to a certain range, you might not be able to reach that range without losing some of your linearity, right? So you can see that there are many trade-offs that you need to work with when you are designing those analog electronic circuits, analog RF electronic circuits. And the whole deal here is, because of those too much complexity, CAD tools are an essential tool at this process, right? So if you want really to design something, عليكم السلام ورحمة الله. عليكم السلام.
We didn't want to bother the class.
Right, okay. Try to come early, not to bother. طيب. So again, eventually, because of the too many trade-offs, typical engineering approach is that in these cases, to get something efficient, modern, up-to-date, use simulation tools or use CAD design tools eventually, right? So simulation, and then you end up with production coming from CAD tools. Because doing this by calculation, with the era that we live in and the too many requirements and the too many trade-offs, becomes almost impossible. However, we will learn in this course a little bit to understanding of each one of those. How does it look like? Where does it come from? How do we take care of it? But we're not going to do a design by paper and pencil, right? We're going to hopefully do a design by using CAD tools, okay? Yes?
What are the most, from the trade-offs, which are the most?
The most critical ones.
No, the most that we can trade off, like leave it out.
No such a thing. It all depends on your application requirement, right? If you are designing something for a cell phone, which is desired to be very compact, very low power consumption, then these will become your critical aspects, right? If you are designing something for military, you don't care that much about the power consumption. Maybe it's going to be powered by huge batteries carried on a car or whatever. The most important part is going to be probably noise. You don't want that much noise. You want it very reliable because it's critical for communication and command and so on. So it all depends on how do you play within those trade-offs. It's going to be dependent on the requirements of what you are designing. Okay? And this will tell you what you can give a little bit away and what you can gain in return. Okay? But that's a very good question. Okay? So the target eventually is to have very high performance, very low cost, high efficiency, and increased functionality. You can do more and more in terms of the functionality. Again, you cannot achieve all of those with the maximum possible, right? You have to give up on some of them to gain on the others, depending on the requirements of your application. طيب, given that this is the story, that these are the challenges, that the fact that we need to really overcome, how does the big picture of RF communication looks like? I think we discussed this last time, but I'm going to repeat it in a more structured way right now. So the overall story here is that you have some information, and you want to send that information typically what we are dealing with here is a wireless communication system. So you need to send it through an antenna, and then the receiver side is going to have an antenna receiving very weak signal because it has been traveling over a non-friendly medium that causes a lot of power losses. So you end up with very weak signal here received by an antenna, and you want the other side to receive the same information, right? That was transmitted from here. عليكم السلام ورحمة الله وبركاته. كان في امتحانات ولا حاجة؟
لا نسيت شنطتي في المترو.
Okay, so remember, also we discussed this last time. The first thing that comes into mind is this signal is going to travel through an unfriendly medium. So I need probably to put a lot of power in it to make sure that it reaches where I want it to reach, right? So the first thing that comes in mind that I need to amplify this signal. That's the first thing, okay? And that's very intuitive, right? Similarly, we know that the signal here is going to reach with very weak, on the receiver side, is going to reach with very weak power value, or if you think about voltage, so amplitude value. And typically to process it through the rest of my electronics, I need to boost its amplitude or voltage or power value. So I need some amplifier again at the receiver side, okay? However, the requirements of those two amplifiers are very different. The one that I need at the transmitter requires really to be as linear as possible with very high dynamic range. I want to put a lot of power into the signal, right? So we call that a power amplifier. And because I'm dealing with very high signal power values, I don't care that much about the noise because the noise is going to be really a negligible component, okay? So I don't care when I'm designing this amplifier on using electronic design techniques that reduces the noise. I care more about linearity and dynamic range, ability to amplify to a very high power value without losing linearity, right? So these are the requirements for the power amplifier. Now when it comes to the amplifier at the receiver, what's the real challenge? The real challenge is that I'm receiving really a very, very weak signal, right? And I need to amplify it still so that I can drive the rest of my electronics, because if it stays very weak, the rest of my electronics will not be able to process it, right? So I need an amplifier, but in this case, because the signal is very weak, I have to be careful not to add too much noise to it. Because if the noise level matches or exceeds the signal level after a certain threshold, nobody is going to be able to detect that signal anymore. It's going to be hidden inside the noise, right? The noise is going to overcome the value of my actual signal. So I need here to amplify without adding too much noise, and I don't really need to amplify to a huge power range because the rest of my components here that are going to process the signal are wired connected close to each other in a very small space, right? So they are not going to cause that much power loss, but they will be affected a lot if it gets some noise here. So this amplifier at the receiver side needs to be designed with low noise into consideration. So your design here does not require that much dynamic range. You can really control the output voltage to be even in millivolts, that's fine. A little bit higher in 1 volt or 2 volt, that's fine. You don't need that much big power at the output, but you want to make sure that your electronics that are composing the amplifier does not add much noise to the signal because the signal is already weak, okay? If it adds much noise, it will hide the signal and no gain is gonna be achieved from amplifying it, because amplifying it with a lot of noise is gonna cause nothing. It can not allow you to differentiate the signal from the noise, okay? So here we call it a low noise amplifier at the receiver side. So and they are two different designs, okay? Now in addition, last time we discussed also that our signal is going through an antenna, and we figured out that if you remember from your electromagnetics, if you studied antennas in electromagnetics or maybe from your physics background, that the dimension of the antenna is proportional to the wavelength. And we have seen that if you want, for example, to send plain voice signal as it is, which occupies a frequency of about 3 kilohertz, right? Over an antenna, you need an antenna of approximately 8 to 10 kilometers, right? Imagine an antenna like 10, you are dragging a 10 kilometer antenna behind you to be able to transmit. Would not work. What's the solution? The only solution is to reduce the wavelength. How can I reduce the wavelength? I have to increase the frequency, right? So we figured out already that in addition to the obvious amplification that we need, we need also something to move the signal up in the frequency. That's why we call that an up converter, because it takes the signal through higher frequency to an upper frequency. Okay, that's the same as what we call a modulator. Okay, so modulator or up converter are two names of the same device. Okay, now if I have converted my signal to a different frequency, I've changed the nature of the signal, right? So now if I leave it as it is after amplification and try to take it at the receiver, I'm not going to be able to listen to anything. It's a completely different signal because its frequency has changed, right? So I need to bring it back to its original nature. This is why I need a down converter to bring it back to its original frequency range, such that it comes back to its nature, whether it's a video, a picture, an audio, whatever. I can see it, I can hear it, I can read it, whatever. Okay? So that's why we also need at the receiver side a down converter, which is also called a demodulator. Yes?
Doctor, in some cases they bring it down all the way to 0 hertz.
هو 0 هرتز هو ده البيس باند اللي هو الاوريجينال of the signal. Any original signal, whether it's whatever, any original natural signal is centered around 0. Now when you up convert it, you take it away from 0. Now again, a signal itself occupies a band, right? But when we talk about the frequency that we use for designing antenna or for this or for that, we are talking about the center, the middle value of that signal. Okay? If you probably, the second part of your question was that in some cases they don't bring it to 0. They bring it, that has to do later on with the architecture of those. There is something called direct conversion, there is something called heterodyne conversion, there is something called conversion with intermediate frequency. All of these eventually, from input to output, they take a signal at a high frequency and they bring it back to its original 0 centered frequency. Okay? But what happens in the middle is something else that we will go through as we go through the design of those. That brings me to the fact that when we are talking about down converters and up converters, right, there are other requirements here, right? Might not see it here, but it's an implicit requirement. In order to convert a signal to some higher frequency or to bring it back to the lower frequency, I need something that generates that higher frequency. It does not exist here, right? It's not in the signal. So how can I get it to a higher frequency? I need some oscillator, frequency generator. That's again a basic component that exists in every RF electronics transceiver circuit. And based on that, we can take this story of RF communication and come up with a big picture story of an RF transceiver. A transceiver is a transmitter and a receiver. Most of the devices that you use, except very few, most of them, they do both functionalities. So your Wi-Fi card inside your iPad or laptop or tablet or whatever has a transmitter and a receiver. Your cell phone has a transmitter and a receiver for the 4G, 5G, and the cellular. Also has a transmitter and receiver for the Bluetooth port, and it has a transmitter and receiver for the Wi-Fi, and so on. So typically, we design transmitters and receivers into one circuit. We don't really separate them, except in very few, mostly experimental cases. Okay? But typically, we have transmitters and receivers in the same device. The combination of a transmitter and a receiver is called a transceiver. And as we have seen from what we discussed about the RF communication system, general or overall big picture or story, we can imagine that the block diagram of a transceiver would look like something that we see here. Don't forget that, okay? We don't really care here about the digital baseband part. This is discussed, I mentioned that already in the previous lecture. This is discussed in other courses, such as the digital communication in terms of concepts, or you go for digital design. It's not an analog RF design for this part if you want to design an actual transceiver. So you do that using digital design techniques, not an analog design system. So that's something outside the scope, but in a general transceiver, it exists. We typically have a digital baseband processor, right? Except very classical communication systems like the pure AM that's used for, or pure FM that's used for radio and so on. And these are phased out systems that are being phased out by time, right? But all modern communication systems are digital communication systems, so they have this digital baseband part. And before that, of course, you have some source of information. Our typical information is a physical phenomena, something that you can see, something that you can hear, something that you can read, whatever. So these are typically analog, and then they get converted to digital. They go through the digital baseband processor, and then they have to be converted for the transmitter side of the story. They have to be converted to analog again. They go through the up conversion, the power amplifier, the antenna. For the reception, it's the opposite. I receive a very weak signal through the antenna, goes through low noise amplifier, becomes amplified here, goes through the down conversion, so bring it back to its original format in the frequency domain, and then analog to digital so that it can be processed in the baseband, and then eventually digital to analog, and then displayed to the user or sent to the user. What's your question?
Will we need to deal with it in projects?
With what?
The digital part?
No. So in all what we will do, in all شباب اللي عنده لا اتفضل اسال عندك question تمام
Satellite TV, does it have digital plus?
Yes, satellite TV is digital. All satellite TVs are digital based, and they have different standard. DVB, which is the digital video broadcast standard, terrestrial, and satellite. So terrestrial, there is some local satellite TV broadcast which is done in a different way, and there is the one that comes directly from the satellite. Okay, so all of it is digital.
So when we say digital, it's like working with MPV files, like MP4 files. Does it have a processing?
It's not necessarily the format of the file that you see. When we say digital, we mean that the signal which is coming. Now imagine the story of the satellite TV. You have a station which is probably took the videos or whatever. Let's take the story of the live broadcast. Okay, so you are broadcasting live from somewhere right now. Okay, you have the camera. The camera is an analog device. It takes the picture, at least the lens and the parts, right? At some point, the information is converted to digital. Whether the camera converts it into digital and then passes it into the broadcasting equipment, or the camera is still analog and it's connected with an analog link, RBG for example, to the broadcasting station. Now the broadcasting station takes that signal, digitizes it, does some processing on it for communication. This is the digital baseband processor, right? And then it has to convert it to analog to be up converted and amplified and all these things. So it goes through this conversion, and then up converted, power amplified, transmitted to the satellite. The satellite is going to take the signal as it is and relays it back to your receiver. Your receiver is going to be this part. So it will go through low noise amplifier, down conversion, so it brings it back to its original frequency. And then it's converted to digital in your receiver, inside the receiver, after the cable that goes inside the receiver. And they're processed somehow. And then eventually it goes to the TV, either digital through HDMI link, or sometimes analog if you have an older TV link, right? Yes, and if it goes to the TV, eventually it's converted to analog so you can see it, right? So it's some analog picture that you see on the TV, right? So the internals of the communication includes a digital communication system, okay? Any other questions, Shabab? Yes?
Are we going to be discussing IQ signals, or that's part of
Not at all. IQ signals have two meanings. We are going to discuss that we will use in this up conversion and down conversion two carriers. The original carrier, let's say a cosine, and then a phase shifted one. That's always the case in almost all modern communication systems, right? Because that's a resource available for you. Why not use it, right? Okay. So, but we are not going to discuss the IQ in terms of symbols that are used for digital modulation. Also, we are not really going to discuss those. So we will not discuss the analog to digital and digital to analog converter part of this system. We will mainly discuss up conversion, power amplification, and beyond until the antenna, right? And similarly in the receiver side. We are not going to discuss analog to digital. Analog to digital typically belongs, I mean, you can discuss it in this course, but the time will not allow the amount of information that we have to go through. And typically also it's discussed in general analog electronic courses. They don't have to be RF electronics, right? Because again, here you are dealing with a signal without being really brought up to higher frequency or higher power or anything. So it's typical analog electronic devices. Or they can call them actually mixed signal devices because they have a digital side and an analog side, right? So they are even more complicated than typical analog devices. So we're not going to go through the modulators, the analog to digital and digital to analog. Okay. Even so, if you work in analog RF, you might be really, many of the new innovations come in this part, by the way, of RF electronic devices. But anyways, we're not going to discuss it in this course. It's too advanced for this course, okay? One thing is, as I mentioned, in order to do the up conversion and the down conversion, you end up with a necessity to be able to create a sinusoid, right? The device that creates a sinusoid is called an oscillator, right? But then you are not always hardwired to a single frequency that you want to generate. You want some flexibility in your device. For example, your radio receiver in the car, it allows you to receive multiple channels. You can tune it, right?
Yeah.
So in that case, your oscillator is not really fixed to a single carrier value. You can tune it to different carrier values. In order to be able to do that tuning of the oscillator, changing the center frequency to some desired center frequency, use something called frequency synthesizer, which allows you to tune your oscillator frequency. So it's not a fixed frequency, it's a variable. You can change it, similar to a variable resistor, right?
Yeah, but a capacitor in this case. Usually capacitor, yes.
Yes, in the simplest form.
Yeah.
But in other more complicated forms, there are other architectures for that. Yes. Okay. This is the story. So in this RF transceiver, signals are, of course, amplified, but they are up converted or down converted. So they are up converted in the transmitter, down converted in the receiver, using an oscillator, which is controlled by frequency synthesizer, and may occasionally need some filtering somewhere inside these circuits, the up and down converter, and sometimes even outside them. Okay, it's not shown here, but filtering is going to appear almost in many of these stages of our transceiver designs, right? So just one more important thing to mention here is when we talk about up converters and down converters, right? We are going to talk about first different architectures that are used to do those, the super heterodyne, the direct conversion, and all of these typical architectures. Architectures means what are the different components and how the up conversion and down conversion is happening. Is it in a single stage, multiple stages? Why do it in a single stage? Why do it in multiple stages? Advantages and disadvantages. And then accordingly, based on that functional block diagram of each one of them, we can figure out the circuitry needed to implement that in terms of electronics. And then in addition to the architectures, we are going to talk about the device or the circuit design, right? That applies for both of them. So here also we have architecture and device level discussion or circuit level discussion, okay? That's very specific for those because these are kind of the heart of the RF communication system, the up converter and down converter. Power amplifiers are more straightforward, even though challenging, but they are more straightforward. And oscillators are also more straightforward devices, even though understanding them is not easy in some cases. But the most critical part where also some of the innovation can happen in different stages of advancement of communication system are the architectures of the up converters and down converters, because they affect the performance a lot. Having that said, I think I am done of what I need to discuss today. It's not a very long lecture, but just gives you heads up to what we are going to, and then next time we will hit the wall. So now we are just walking slowly. Next time we will go through the real meat of the course. Again, the outcome of today's lecture is that RF design is challenging due to two reasons. The multidisciplinarity involved in the process, right? Because you need to capitalize on your knowledge in several electronics, communication systems, some of the knowledge that you got in signals and systems, some of the knowledge that you got in your electromagnetics. You need, and even circuits, by the way, because we'll have lots of like connectivity here. Some capacitors connected with some diodes connected with some resistors and so on. So even your circuits course, you will still be using that. And the other challenge is the too many trade-offs that you have to deal with, okay? General RF transceiver needs to perform the following functions as key functions: amplification, up and down conversion, which is modulation and demodulation, generation of sinusoids using synthesizers, so tunable sinusoids, and finally filtering. As we go through the sinusoid generation, we will encounter a challenge that we will go later on. I'm not going to discuss it much, but I'll just give you a heads up about it. How to make sure that the sinusoid that you generate at the receiver is synchronized with the one generated at the transmitter, both in terms of its frequency and in terms of its phase, because a phase shift or a frequency deviation will cause bad effects to the signal. So how do you do that? Because these are two separate devices, right? How do you make sure that one of them is synchronized with the other? We might discuss that a little bit more details, but at least we will discuss the PLL, the phase lock loop, okay? In terms of designing them as part of the essential components in RF transceivers. Next time, when we start hitting the wall, we'll talk about units. So again, we will remind you of the dB, dBm, and those different scales. And then we'll go about to discuss the nonlinearity effect, extra harmonics, mixing of harmonics, and so on. And then we'll discuss how to represent noise and what's the bad effect of noise on transmission systems. And last but not least, we'll discuss something called the sensitivity and the dynamic range. Dynamic range has to do with amplifiers. Sensitivity has to do with low noise amplifiers and how much signal they can actually, how low is the signal that they can detect due to the explicit or implicit noise effect. Okay? So these are the things that we discussed. These are the key challenges. These are all in chapter 2. We're not going to cover the whole chapter. The whole chapter includes many other things like two-port network representations and scattering and all these effects, but we are not going to go through them. We will only go through these. These are the essential ones. And the other ones, probably, if you study more advanced or you want to learn more about this, you can do them yourself. But we are not going to go through them. Okay? Any questions so far? طيب. Tool for